look for recordings up on Classroom. I probably will have enough time to get them up over the weekend. So do keep an eye out for that. Yeah. So I guess I would like to add one little extra wrinkle, which is that we had been working with actual amounts, number of grams of a substance, but we can actually find empirical and molecular formulas from just percentage compositions. We don't even need to have the amount of grams. So I wanted to give you guys an example of how to do that and then set you loose on a few practice problems yourself that we'll do here together in class. So, first things first, and I actually I took this particular problem from the textbook because I kind of liked it. So it's one of their example problems. The bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of 27.29% carbon and 72.71% oxygen. What is the empirical formula for this gas? So you'll notice the only really difference between what we had been doing before and this is that instead of having a certain number of grams of carbon and a certain number of grams of oxygen, we just have percents. And it might feel a little bit like, well, how do we even start this? How do we turn from percents to grams? So we can actually kind of arbitrarily assume that the total mass of our sample in grams is honestly anything we want. We could assume it's 33.78 grams. We could assume it's, pick your favorite number. 42 is the answer to life, the universe, and everything. But I think by far the easiest thing to choose is 100 grams. If we say that our sample is 100 grams, then the number of grams of each substance that we have percents of are just the same number as the percent, right? 27.29% of 100 is 27.29. So this would give us 27.29 grams of carbon and 72.71 grams of oxygen. I mean, if you always assume that your sample is 100 grams, which is totally valid to do here, then you have to do no math. You just take that number that you were given, basically. And then from this point, we can now do our whole procedure, right? Which is, so now that we have the number of grams of a substance, we want to convert this to number of moles of a substance, which will tell us basically the number of atoms. So to convert this to moles, we want to take our 27.29 grams for carbon, and we want to divide by carbon's molar mass, so the grams per mole. For carbon, I believe we should remember, at least I remember because I've done it so many times, it's 12.011 grams per mole. And for oxygen down here, we take our 72.71 grams and divide by oxygen's molar mass, which is 15.999 grams per mole. And so all that being said, I can even plug this into my calculator, and we'll figure out the number of moles of carbon and of oxygen. So let's see. 27.29 over 12.011 gives us 2.272. moles of carbon. And for oxygen, 72.71 divided by 15.999 gives us 4.54. If I round it up, it's 545 moles of oxygen. And so our standard thing would be to take these numbers and put them in a little formula like this. And then we divide by whichever one is smaller. In this case, it's 2.272. And just to be really precise, I'm going to take the exact numbers I have in my calculator from doing these calculations and divide them.
Secondary.
Uh-huh.
Sorry for interrupting. I have a quick question.
Absolutely.
So when you're when you're coming from 27.29 grams,
Mm-hmm.
where do you get the number 12.011 grams?
So that is the molar mass of carbon, or honestly, the atomic mass of carbon. Let me do a second screen share so you can see it.
And can we just like look that up, or is that?
Yes, that is absolutely something you'd look up, and you look it up here on the periodic table. I hope you guys can see this.
Yeah, we can.
Yeah. So here's carbon.
Oh,
Its
cool.
atomic mass is 12.011. That's usually an AMU, right? Um, yeah, I guess you can't change the unit here for this, but yeah, there's its atomic mass, and as we know, the number of AMU for the element is going to be the same number of grams per mole, and then there's oxygens right there as well. So yeah, that you would have to look these up though. I mean, unless I have used them so many times now that I am just starting to memorize them, but I would expect you to look them up. I wouldn't expect you to try to memorize these. There's a lot to remember.
Thank you.
Yeah. So we do this division. I get, obviously for this one it's 1, right? But divided by itself. For oxygen here, it is 2.0002. I'm going to round that to 2, to be honest with you, because it's very close to 2. And that gets us an empirical formula, at least, of CO2. And given that CO2 is a real molecule that we know pretty well, I'm going to guess this is also the molecular formula. We don't have enough information to verify that, but we're talking about the fermentation of alcohol, right? Basically, we're producing ethanol. Fermentation of grain to produce ethanol, yeah. So I know for a fact that this is the actual gas that is produced, CO2. So that's just a simple example. This is exactly the procedure we have used before, and it's just one extra step of converting these percents into grams. You could do this any way you want, right? You could assume the total mass is anything you want. You could assume the total mass is, I don't know, 62.83 grams. If you were feeling particularly weird that day, there's no particular reason to choose this number. But you'd find out what 27.29% of 62.83 is, and that'd be your grams of carbon. You'd find out what 72.71% of 62.83 grams is, and that'd be your particular amount of oxygen. I don't know why you would choose anything other than 100, right? It makes the math so easy. So there you have it. How are we feeling about this? Let's get just a quick temperature check. And then I'm going to set you guys loose on an example problem. Oh, and I don't have chat open. I'm sorry. I need to be able to look at your chats. We feeling okay, though? We feeling like at least we can try these problems? Maybe we won't get them right all the time, but we'll at least have a chance of knowing the procedure. I think we need to practice, yeah? So I'm going to give you another example. Just like this one above, like exactly like it. Our sample is 40.0% carbon, 6.71% hydrogen, and 53.28% oxygen. So let's practice this. Let's do our best trying to figure out what at least our empirical formula is. And then that being said, if you get to an answer, whatever your answer is, type it to me in chat. Do like a private chat to me, and we'll see. And maybe I'll give you guys maybe till 10:55, 10 minutes to try it. Yeah. Give it a shot. Let's see what you can do. And I'll be quiet so you guys can work. Okay, so I think it seems like most people have got it. Oh, yeah, Everett. There we go. So it seems like most people have got it. Does anyone still want to take a minute to work on it, or do you want me to go through it? Go through it. Oh, I'm really quiet all of a sudden. I think it's because I accidentally hit my mic gain knob. So is that better? Should be louder there. Cool. I think I hit the knob a little bit, and I didn't return it back to its original position. That should be nicer.
I think
Yeah.
looking at the previous problem, what I did on this problem, I find some of two totally different answers. So, are you supposed to divide 7 points? Oh, I'm sorry. Actually, never mind. It's totally different. Never mind.
Oh, okay. Do you want me to go through this one right now?
Yes, please. That'd be great.
Yeah. Okay, I will go through it. So, just the same as we had up here. C, H, and O. We're going to assume that we have 100 grams total mass of our compound. So that means that we basically have 40.0 grams of carbon, 6.71 grams of hydrogen, and 53.28 grams of oxygen. And we can convert these to moles using the molar masses. We know carbon and oxygen already, and hydrogen is pretty easy to look up. 40.0 grams of carbon divided by 12.011 grams per mole for carbon gives us, I'll have to do that division, 3.330 moles of carbon. For hydrogen, 6.71 grams of hydrogen, and its molar mass is 1.008 grams per mole. It's going to give us 6.65, if I round, 6.657. $6.656746. And then for oxygen, 53.28 grams of oxygen divided by our 15.999 grams per mole gets us 3.330. Hey. Moles of oxygen. It just so happens that these two numbers are identical. I mean, it's out to 7th decimal place. They're the same number, right? We get a sort of a preliminary formula that looks like so these two are exactly the same number, and they are both the smallest number, so we're going to divide by that. So our 6.656746032 divided by our 3.330, I get 1.99889789. You get the picture. It's 2. So I get a C, 1C, H2O, 1 oxygen. And that is our empirical formula. And I think almost everyone had that. I think, in fact, everyone had that. Anyone that put in the answers. Yes, Elena, of course. Very nicely done. So, I think we had some really good success with that. So you guys, I think you guys are doing really well. You ready to get set loose on another one, a third one? I have 2 more, at least, and maybe I can go hunt up a fourth or a third.
I have a quick question.
Absolutely. Ask away.
So, I understand that. My question is, why is there 2, okay, I understand it, right.
Oh,
I just had to take a minute to look at it, sorry.
okay. No, it's good. Sometimes asking the question gets you to think about it a little bit, and then you realize you actually know it. I love it. How about another one from the book? I'm going to keep switching my colors up here. So nicotine, which is the addictive thing in cigarettes, contains... Whoops. Where's my pen? There it is. 74 0.02% carbon, 8.710% hydrogen, and 17.27% nitrogen. So let's do this part first. Let's just find what the empirical formula is first. And then I also have the extra information needed to find the actual molecular formula. So go ahead and give that a try. We'll see where we get to. Okay. I think everyone has had a good chance to do this guy. So let's try solving it. Unless if you want me to stop, tell me right now and I will give you some extra time to keep solving. Emiliano's dancing. He's having a good time. Oh, you can't see me, but yeah, I'm dancing too. Oh, Anna, you're actually, your original answer was closer. It's twice. You had twice the empirical formula. So yeah, we'll get there. And actually, it turns out the formula you got is going to be the final answer, the actual molecular formula. So let's do this. Let's convert these from percents to grams by assuming that there's 100 total grams of the substance. 74.02 grams of carbon, 8.71 grams of hydrogen, and 17.27 grams of nitrogen. For carbon, we know it well. 74.02 divided by our 12.011. I'm dropping the units here because I'm lazy. That's not a good thing. I should provide a good example. 74.02 grams and 12.011 grams per mole. Try to avoid laziness. 6.16268, so 6.163. Hydrogen, it's going to be pretty close to 8. $8.641. And then for nitrogen, 17.27 grams of nitrogen. Its molar mass, we have not seen it yet today, but we can look it up. 14.007 grams per mole is nitrogen's molar mass. So 1.233. Okay. Got the chat. All right. There we are. Oh, and you know what? I have chat up. I need to have my participants tab up just in case someone gets kicked out for some reason and I don't see and they're trying to come back in. I have done that before. Okay, so here is our number of moles. So we have I put an H. This should be an N. My apologies. The smallest number is the 1.233, right? We're going to divide by that. And what we end up getting is, let's see, I get 7.008 for H. That's going to be a 7. Nitrogen will be a 1. And for carbon, it's going to be pretty close to 6. Sorry, 5. 4.998. That's a 5. C5H7N, which I think is what almost everyone got. So here's our empirical formula, at least. I think I misspelled that. I think it should be I empirical formula. So that's the empirical formula. But if we want to get the actual formula, we need the extra information about the actual mass of this molecule, right? So our extra information given to us is that this molecule had, let's see, 40.57 grams of this molecule has 0.25, the book gives us 0.2500 moles of the substance, right? So it's a little bit obtuse here, but if we just divide this, 40.57 divided by 0.25, that'll give us the grams per mole of the substance, the molar mass. 40.57 over 0.25 is 162.28 grams per mole. Okay. So we have this information, this extra information. Does anyone remember? Boy, I really made a mess of that. 162.28. 162.28. Just to rewrite it, just so you guys can actually read it. Does anyone remember? We did go over this, but it was sort of hurried at the end of last class. How do you go from this empirical formula and using this information to the actual molecular formula? Anyone have clue?
An idea?
Uh-huh. Yeah.
Should you add up the, what do you say, the mass times the amount of atoms in the molecule to get?
Yep. To get the actual mass of this formula?
Yeah.
Absolutely. And then you divide this divided by the mass of this formula will get you some number. And then you'll multiply all the numbers in this formula by that number. Lola asks in chat, where did you get the 0.25 mole? That's just given in the problem. These two numbers, the 40.57 and the 0.25, those are just something the problem tells you. There's no way to like derive that. Yeah, to use GeoGebra to keep track of the numbers is a smart idea. I keep track of the numbers on my graphing. Oh, you can't see me. I have a graphing calculator. Maybe I could. Hold on, give me a second. I will switch myself back on. For just a second. And I'm gonna. So I have a graphing calculator, right? I don't know if does anyone else have this kind of thing. But I keep track of my numbers in here, right? And say, for example, I have my 162.28 here, and I want to use that again. If it's the last thing that I just hit enter for, I can just hit, if I want to multiply by something, I just hit times, and it automatically puts up answer times. So yeah, that's nice. Or if it's further up, right? If I want to use the 4.998 that I got before, I can just scroll up to it with my arrow button and hit enter, and it'll put it down there, right? So if you have this kind of graphing calculator, you can do that with it. Alex says, yep, I believe that's it, Alex. Beautifully done. I'm going to go back to sharing my screen. If you guys would like to take a crack at finding this molecular formula, Alex just got it, which is awesome. Love to see it. Okay. It's 11:15. We've got 15 minutes left in class. Is anyone still working on this this molecular formula here, or would you like me to solve it right away?
I'm still working on it, but you can start it.
Okay, I'll start it. And we'll see where we get to. So we want to basically compare this mass, grams per mole here, to the mass of whatever this formula is going to be in grams per mole. So we go back to our little table that we had a while ago. C, H, and N are our three elements. My straight line drawing skills are trash as ever. The mass of each of these in AMU, we actually know these already because we just looked them up. 12.011 for carbon, 1.008 for hydrogen, and 14.007 for nitrogen. The numbers in the formula, anyway, there's 5 carbons, 7 hydrogens, and 1 nitrogen. And then the total mass in AMU, we just need to multiply these. So nitrogen's the easy one. 14.007 times 1 is 14.007. Hydrogen, 1.008 times 7. If I was more awake and I had had more coffee this morning, I could do this in my head. But I am feeling kind of sleepy, so I'm going to plug it into a calculator. 1.008 times 7 gives us 7.056. And 12.011 times 5. Again, it's not too hard math-wise, but I am a little bit sleepy. 60.055 is what we're going to get there. So we add these 3 together. Whoops, I'm adding it to itself. Add these 3 together, we get 81.118 AMU. So that's the mass of one molecule of this formula. So its molar mass is that same number, 81.118 grams per mole. Then what we do is we take this number that we just got, and we take this number that we have given to us by the problem, and we divide. So the given number of the actual molecule divided by our formula mass will give us a number. And in this case, the units cancel out. So this is a unitless number. It's just a sort of a number floating free. 162.28 divided by our 81. It gives us 2.00054. It's 2. It's 2. And so this number here that we just got from doing this division, we go through this formula, and if we want to do it really technically, we put the formula in parentheses here, C5H7N, and we multiply we multiply by 2. All right, so all the numbers in this formula, 5, 7, and then a 1, are going to get multiplied by 2. So we're going to get to C10H14N2, and that is our molecule. How did I get the 44.57 grams? That is actually given in the problem. That is just stated as part of the problem. It says, if 40.57 grams of nicotine contains 0.25 moles of nicotine, what is the molecular formula? So, I didn't get it. They gave it to me. Very kind of them, right? All right, we have 11 minutes left in class. Take a minute to copy this. Make sure you got it all down really nicely. And I have one final question for you guys to try out and see if you can get it. And then I'll set you loose on the homework. Exciting, right? Okay, I'm going to start a little new page here. If you want me to stop so you can copy down, just shout out. Oh, I think people are still copying. That's okay. Take your time. No need to rush. Okay, I'm going to start up a new page here. And I'll give you the last problem. The last problem is this. It's a mystery molecule, which has a composition of 49.47% carbon, 5.201% hydrogen, 28.84% nitrogen, and 16.48% oxygen. And you also know that the molar mass of the substance is 194.2 grams per mole. So using these pieces of information, figure out the actual molecular formula of this nice molecule. We've got 2 minutes left, so I'm actually just gonna start doing this. Keep working, but I'm gonna just start going through this really quick. I've actually done all the calculations already on my calculator here, so I'm not gonna even worry about that. So 49.47 grams of carbon over its 12.011 grams per mole gives us 4.119 moles of carbon, 5.201 grams of hydrogen over this 1.008 grams per mole gives us 0.16 if I round. Lola? Yep. Elena, that is the empirical formula, so you're almost there. 28.84 grams of nitrogen over its 14.007 grams per mole is giving us, what is that, 2.059 moles of nitrogen and 16.48 grams of oxygen divided by its 15.999 grams per mole. Well, there's someone at my door. Gives us, it's like 1.030 moles of oxygen. So those are our moles. So is that a 9? 5.9? Yeah. So we divide by the smallest, the 1.030. And with various rounding, we get to C4H5N2O. Given that this is 1.03, right, it's going to be really close to these numbers already. So that's all we've got. So the mass of this particular compound, CHNO, mass in AMU, we know this already. We've already used these numbers. 12.011, 1.008, 14.007, and 15.999. There's 1 oxygen, 2 nitrogens, 5 hydrogens, and 4 carbons. So this gives us 48.044 grams, AMU, sorry, of carbon. It's going to be 5.0. Oh dear, I lost it. 5.0. I forget. I don't even remember what it is. Oh god, we're already well over. Okay, don't worry about these. You can calculate these if you want. The actual answer is 97.097 AMU, or grams per mole for this substance. And then we do our division. 194.2 over 97.097 is going to give us 2.0000. What is it actually? 2.0006. It's 2. Right, so we multiply all these guys by 2. Our actual final formula is C8. H10 N4O2. There we have it. Okay. So there is a homework, everybody. It is up on Classroom. It's due a week from today at the start of class, so Friday. It's all this stuff. There's 3 problems, and I try to increase them in complexity as they go. So the first one's easier, the third one's harder. And yeah, let's try at least to have practiced it, or at least attempted it by Monday, or Tuesday, I guess, is our first. I guess we don't have class Monday the next week, I guess. I just noticed that when I was looking at calendar. So yeah, let's try at least to have class, to have it attempted by next class. Yeah, see if we can get that done. You guys feeling good? All right. Well, have a great weekend, and I will see you guys all on the flip side.
Thank you.
Thank you.
Thank you. Have a good week.
Have a good weekend.